Good morning. This lesson introduces the burgeoning topic of building electrification. We're going to look at some of the possibilities and challenges about this kind of important movement to find alternatives for powering our buildings besides the common use of fossil fuels. The lesson is going to cover a few points here as an overview. It's going to introduce the goals of building electrification, the opportunities and challenges associated with that. We're also going to look at the production and distribution of electricity in both the national and global energy markets. And we'll do then an introduction to electrical systems in buildings, a big topic in its own right. And then we'll review some electricity basics in regards to power and consumption, which influence how we choose to switch over to all electric buildings. And then we're going to look at a few key design areas where as architects, our efforts towards promoting building electrification can be focused. So our first section of the lesson will be an introduction to the goals of building electrification, the opportunities inherent in it, and the challenges that it faces. Building electrification is sometimes also known as beneficial electrification or building decarbonization. And it describes a shift to using electricity rather than burning fossil fuels like oil, gas, and coal for heating and cooking. The ultimate goal is an all-electric buildings powered by solar, wind, and other sources of zero-carbon electricity. We've got some work to do to get there. If you look at this chart right here, you can see the evolution of the electricity generation in the United States over about the last 10 years or so. And you can see that we're still at a point where about only 25% of our electrical production comes from renewable energy sources. Beneficial electrification also refers to using technologies such as electric vehicles or electric heat pumps that operate with electricity instead of burning fossil fuels. Electrification function as a decarbonization strategy. When electricity is used, or is on a path to being used, generated with clean resources such as wind and solar power. According to the U.S. Energy Information Administration, the carbon intensity of electricity will decrease more than 26% from 2020 to 2050. And if you refer back to our chart that we just looked at, that isn't a whole lot of progress. We can do better. Applying electrification to buildings means using electricity for core functions such as heating, cooling, and cooking, and potentially industrial processes that have traditionally been provided by on-site combustion of gas, heating oil, propane, and other fossil fuels. Specific to building technologies that are driving electrification as a viable solution include air source heat pumps and geothermal heat pumps, which Professor Younghans has introduced to you, induction cooktops and stoves, which are replacing natural gas stoves and ovens, and also high efficiency electric or heat pump water heaters, and of course, electric vehicles. Government and local incentives and funding programs to replace on-site fossil fuel equipment with electrical equipment are growing rapidly. Some jurisdictions are adopting policies or codes to require new buildings to be all electric and or to restrict new on-site fossil fuel use. These are referred to as gas bans, as a means to halt further expansion of fossil fuel infrastructure and avoid the future cost of replacement to all electric. Berkeley, California was the first U.S. city to ban new natural gas building infrastructure in 2020. The ordinance includes all new construction except for building additions and remodeling projects. Developers, builders, and owners of new structures must find alternatives to natural gas for heating spaces, drying clothes, cooking, and heating water. And here you'll find on the PDF that accompanies this lesson a link to the Berkeley Ordinance itself, which describes the gas ban that the city implemented. Closer to home, in November of 2022, Ann Arbor City Council proposed a ban on natural gas stoves in new constructions, but the proposed ban does not yet include heating and air conditioning equipment. So it's a step forward, but a small one. Electrification represents a significant shift in the energy economy that will dramatically increase demand on the electrical grid, with a variety of implications in different regions depending on resources and readiness. As a result, many NGOs, including the U.S. Green Building Council, support beneficial electrification, which calls for electrification when it meets the following objectives: that it reduces or at least does not increase energy costs for consumers, particularly low-income households, and that it is coordinated with grid reliability and demand management investments. You can imagine that as we switch over to all electrical energy sourcing for our buildings, that a huge increase in demand for electricity will follow, and the energy grid, which we'll talk about in a little bit, needs to be able to handle that increased demand. Also, that building beneficial electrification reduces harmful emissions at buildings and or from the energy supply itself. In addition, beneficial electrification can help promote energy independence by relying on domestic renewable energy sources. There's a lofty goal in and of itself. Reduces or it does not increase energy costs for consumers, particularly low-income households. This is the Achilles heel of the building electrification program at the moment. Inherently, it's going to involve costs in changing equipment, costs in changing infrastructure, actually even then in costs of the energy itself. We're a country which is awash in natural gas, and it remains our cheapest energy source, even if it's not the ideal energy source for our uses. So switching over to alternatives is going to have a high price tag to it. But as a nation, as a culture, these are goals that are worthy and ones that we should begin investing and acting upon now. Some other opportunities and challenges to building electrification program are equity. Several concerns have emerged related to equity in regards to discussions with building electrification. First, in some areas, electricity is much more costly for heating than natural gas. And while technology is advancing rapidly, electric heat pumps, such as introduced to you by Professor Younghans, may be expensive to operate in cold climates, particularly without updated building envelopes. We're talking about changing our entire building culture, and this is going to have costs to it. It's going to have issues of fairness to it, as the costs are unevenly distributed around our culture, and it's going to take time. Secondly, if relatively higher income households have a greater ability to transition from gas service to all electric homes, the low income customers could be left behind in a shrinking customer pool to support the fixed costs of the gas utility. Jurisdictions need to account for these scenarios in the design of their electrification policies. We hope that the cities of Ann Arbor and Berkeley, both very wealthy communities, are keeping this in mind. Other opportunities and challenges relate to costs. Recent cost-benefit studies indicate that electrification of residential heating and cooling is already life cycle cost effective in some locations and sectors. However, retrofitting some building types, such as tall urban structures, may require more extensive changes to HVAC spaces and those needed within a building, and electrical service upgrades, which may add complexity and cost. Let's strike the word may from this and say we'll definitely add complexity and cost in retrofitting buildings. Much easier, much better to implement these changes at the design of new buildings. And further on this topic of costs, for new construction, avoiding the need to install gas service lines can be a significant cost offset compared to installing electrical lines. Costs of purchasing electrical equipment, such as heat pumps, have generally been higher than their gas counterpoints, but have been declining and will continue to go down as market uptake rises. This will be a slow change. The federal government is also investing to help increase efficiency and reduce costs of some key electrical equipment. These government subsidies are key. In some, costs and benefits are changing rapidly over time and will move towards favoring electrification. Availability. The availability of clean power. Achieving the carbon reduction benefits of electrification relies on clean electricity, which may be provided by on-site renewable energy generation, if you're in an area that has wind, solar, hydroelectric, or clean power from a grid or a community scale project. The pace at which grids in the United States are becoming clean varies widely, and we'll look at this subject in a little bit. On this topic of availability, some grids are inherently low emission through traditional reliance on hydropower or nuclear energy, while others, particularly in the Midwest, may continue to utilize low-cost natural gas or coal plants for several decades. The transition will take some time. Importantly, the time and magnitude of buildings' peak power demands also matter, as a grid that's relatively clean may still use a fossil fuel peaker plant during times of highest demand. A peaker plant is a plant which supplies electricity during high demand periods, such as you can imagine in the middle of summertime when electric demands are very high for air conditioning, or in the wintertime when lighting and heating costs are higher. A building drawing on the grid during those periods will be adding carbon emissions, at least in the near term, if the grid relies on these peaker plants that use fossil fuels. Another challenge to the electrification program is the demand and the increasing demand as we move to an all-electrical building system. Spillover impact, referring to how adding a new demand to a clean grid can cumulatively have an overall effect of requiring more energy to be produced, which may again lead to fossil fuel-based power. So it's a little bit of a conundrum here as we switch over, because temporarily we'll be actually increasing the demand in some areas that we have on fossil fuels as we begin to transition to cleaner fuels. Building grid optimization, as electrification of buildings and transportation adds demand, and optimizing buildings for grid interaction is critical to dampen peak grid demand and peak carbon emissions. This is an area of investment in our infrastructure that for a long time the United States has been unwilling to make under its string of conservative governments. Investing in infrastructure for building electrification and clean energy transmission is key to the success of this program. While metrics are available to specify optimized building characteristics, this is a current gap in our policy. U.S. Green Building Council is advocating for the use of a common grid optimal metrics so we can have efficient and effective measuring across regions, across different aspects of the different areas of the U.S. energy grid. And these can also help guide our policies, and particularly our government incentives to support building electrification. But this notion of demand isn't just related to first world or wealthy countries, as the United States certainly is. The demand for energy is increasing in countries which have long been denied the benefits of many of our new technologies. And how we measure and how we evaluate this increased demand for energy has to take into account this. This is a fascinating article from the New Yorker, which I've made a link to in our course website, Africa's Cold Rush and the Promise of Refrigeration. This is a fascinating article on how both health benefits, economic benefits, educational benefits, and quality of life benefits that we take for granted through our common use of household refrigeration is coming into areas of particularly Central and Southern Africa where it's never been before. It's kind of hard to imagine something that we take for granted is now a new technology in broad areas of the world, but it's true. And we're sometimes blinded by our extreme wealth in our country. And this article puts into perspective some of the benefits, many of the benefits of refrigeration, but also underscores that the demand for increased energy use is also an issue of equity, and that our goals to reduce our energy consumption are side by side with other countries, other cultures, increasing demands for energy that they've long been denied. Electrification is very tied to the whole notion of decarbonization of our energy system. Um, Decarbonization is important because, as we've heard from many sources, building operations are responsible for over 30% of the energy related to CO2 emissions in the U.S. Nearly half of all homes rely on natural gas as their primary heating fuel. That suggests, in many other cases, there could be potentially worse fuels that we use for heating. Heating oil, for instance, still commonly used in the Northeast. Um, so this leads us to ask some questions about electricity's current place in the global energy market. So this part of the lesson will then look at the production and distribution of electricity in the national and global energy markets. So here's a chart which looks at electricity production by source in the world. This is a collective document which looks at where the combined use of different energy sources for producing electricity. And you see on the right that coal still pretty much dominates much of the electricity production compared to other sources. Natural gas, you can see in the purple. Oil, very rarely used because of its expense. Nuclear power, which had once been seen as a panacea, has remained sort of fairly stagnant in its contribution. Hydropower increasing. Solar, as much as we aspire to it, remains limited in its distribution across the world, as well as other renewables such as biomass playing a small role. Wind, you can see, is rapidly increasing as a source for electricity and likely may prove to be one of the more potent renewable energy sources in the United States. So if we look at our overall energy consumption in the U.S., we can see that we've got a long way to go to reduce our reliance on petroleum and natural gas, the two main fossil fuels, as coal continues to drop within the percentage of energy use in this country. But we're still very reliant on petroleum, obviously for our automobiles, and natural gas for our heating and cooking. Oh, but we see over here a breakdown of the renewable energy sources in the U.S., and we see that wind and hydroelectric are the big players, as biofuels and biomass also increase. But there are problems associated with those, both in terms of environmental degradation. But we've got areas of growth, particularly in solar and wind, in this country to take advantage of. Here's this chart again that we looked earlier, and so we can remind ourselves of just how much further we have to develop in our use of renewables within our overall electrical energy generation. Carbon-free electricity is the goal within this, and you can see where the distribution of energy from non-carbon sources breaks down in this pie chart, with nuclear still playing a very large role, despite some of the apprehensions about it, particularly through the 80s and 90s. It's again being considered as a potential source of massive source of electrical energy generation in the country, particularly in areas that don't have the opportunities for hydroelectric, wind, or solar, like the Midwest and the Northeast in particular. What about in other countries? How do other countries fare in terms of their own energy market and their reliance on fossil fuels and new renewable energy sources? In Germany, we see that a country which has made great strides towards developing a green energy system for itself, still has a complex mix of energy sources, reliant to a large extent on coal, burning coal for electricity, and natural gas, but also large investments in development, particularly in wind energy and wind power. Nuclear power still active in the German market, though there are large pressures to reduce or eliminate electric power from the electrical generation grid. Hard coal and brown coal are broken out here as two different components of the electrical mix in Germany for particularly curious reasons here. Instead of showing 30% on the chart, we see two smaller numbers. Hard coal has a greater energy potential. It's the big black chunks of coal we're familiar with. Brown coal, surface mine coal that we have much of in the western United States too, emissions are far worse for the environment. And there's a link here to a discussion about the benefits and detriments of black versus brown coal. There is no clean coal, as many politicians would imagine that we can provide. So it's really a material that we should be moving ourselves away from for various reasons. If we look at the overall mix then of renewables and fossil fuels in Germany from this pie chart here, it looks pretty promising for how things are trending in Europe's largest economy, largest industrial economy as well, with renewables taking up 45% almost of the energy sources. But if we fast forward now to 2022, we see a major change in the energy market in Germany, where renewables have dropped by 50% due to political instability that has altered the balance of fossil fuels versus renewables in the German energy system. Energy is really a global market, and changes in the overall global politics and economies can have an effect on local economies, a drastic one, as we see here, the German economy switching back to reliance on fossil fuels for its energy consumption. Japan, another major industrial economy, is particularly challenged in this regard because of the resources that it has available to itself on the islands. And the country lags behind its adoption of renewable energy sources and remains reliable to a large extent on coal and gas for its electrical generation. The accelerating demand for energy in China has meant both a massive increase in the use of fossil fuel, but the technologies developed in the country also simultaneously provide for an increase in the adoption of renewable energies. So we have a bit of a dichotomy here in the burgeoning country of China, where both sides of the energy puzzle are being developed rapidly. You can see coal plays a huge role in the country's energy, as does petroleum. But other areas are also expanding rapidly in the production of electricity and energy use through renewables. And so the coal-fired emissions from Chinese energy and electricity generation continues to increase, while at the same time that other renewable energy sources, hydropower, solar and wind, and other renewables also are rapidly increasing in China, as we see on the right side of this diagram here. But as with the other industrialized nations in the world, the country has a long way to go in terms of switching from fossil fuels into more renewable energy sources. But a particular challenge with a growing economy, an economy which is evolving rapidly, is both in terms of industrial production, but also urbanization. India, the world's largest democracy, as is known, is still dependent on coal for electric production, but India is making rapid strides with the use of renewables, and particularly from wind, hydroelectric, and solar, particularly hydroelectric, which the country is blessed with many resources for. Um, Increasing energy demands in the country, though, will provide a challenge to these positive developments. Brazil um, is interesting to look at from an energy consumption standpoint for the large and vibrant and growing economy that it is. Um, Very little coal use within the country because very little coal reserves there. Um, but also the opportunity from water sources for hydroelectric power is very large. However, as we know from different environmental news stories, the production of large scale hydroelectric power dams is a drastic environmental um, consequences involved with it. Um, Low scale hydroelectrical generation, small scale hydroelectrical generation, is really one of the burgeoning areas within this technology, um, which requires much smaller dams, but smaller, more distributed hydroelectrical generation with far smaller environmental consequences related to it. As you can see, the projected growth of renewable energy in Brazil has somewhat flatlined based on these projections that we see in these two pie charts between 2020 and 2025 here. As a country is growing and its energy demands increase, it's going to be very important to see how energy production, particularly electrical energy production, can increase without further environmental degradation from the large-scale hydroelectric projects we spoke about. So you can see how the challenges are really clear here as we look at the evolution of the electrical generation in Brazil over the last 20 years, as fossil fuels are actually increasing in their percentage of use in the country due to increased energy demands and the limitations that hydroelectricity has in terms of keeping up with that growth. So Brazil is an important country for us to keep an eye on in terms of how they make their transition into an electrical economy. A positive sign in the United States is that solar power will account for nearly half of new U.S. electrical generating capacity in 2022. However, these sources are mostly located in the West and the Southwest, obviously where the sun is, and in many cases in the American South, and not evenly distributed around the country. However, there are serious incentives both at state level and community level, and even at the university level, as the University of Michigan is committed to a $25 million growth in its solar electrical generation technologies. One thing about the solar electricity programs is that they can be very, very local. They can be at a range of scales to provide energy for recharging a cell phone, for charging a battery on a car, for powering a home, or powering a community, powering buildings. And it is a real area of growth, even in places such as Michigan, where we don't think we have the solar. We don't have enough sun here, actually, compared to places perhaps like Arizona. But I think it is an area definitely with the right incentives that it can begin to take the edge off of fossil fuel reliance in the Midwest. So as we see across this chart here, the mix of energy source in the U.S. has dramatically changed with natural gas replacing more and more coal in electricity production. While still a fossil fuel, natural gas provides considerable benefits over coal and may well prove to be a bridge to the use of more renewable energy sources. With a wider variety of climate zones, the U.S. is in a challenge position nationally for a single source of energy to replace fossil fuels. That's been the attractive thing about natural gas. There's so much of it in the U.S., and it's all over the place and easy to ship. Um, Changes in this country will likely involve an evolving mix of renewable and non-renewable energy sources for the foreseeable future. But as we spoke about earlier, investing now in the equipment in buildings that will provide for electrification is a step to make now as we begin to wean ourselves off of fossil fuels for our electricity generation. We'll have the infrastructure in place to take advantage of that. So let's take a look at a few maps to see about this electrical grid and the distribution of the electricity in the United States. There are a number of major interconnected electricity grids. Interconnected means that the local grid, such as Detroit Edison, is part of a network which is connected to other electrical generating and distributing systems within the country. These grids kind of operate across state lines and are typically heavily regulated by the federal government. You can see that two of the more conservative states in the country, both Florida and Texas, have their own grids, have their own arrangements, truly in order to avoid government oversight. These are the problems that we saw when the large winter storm 2 years ago knocked out the Texas electrical grid for well over a week during freezing temperatures. But we can see that some of these grids are actually international, as we see in the Midwest. Both Canada and the United States are connected together on electrical, a larger interconnectivity grid. It's a grid of grids, so to speak. The power generating facilities in the United States, you can see here as well, are really, as you can imagine, located near the areas of maximum use, densely through the Midwest, along the eastern seaboard, around eastern and central Texas, and in the Sun Belt of California, Arizona, and obviously up in the Northwest as well. And associated with that is an electrical distribution network. Even though some areas of the country don't have access to particular energy sources or renewable energy sources, there are distribution lines to move power from one area to another. And you can see here that these roughly map along with the areas of the interconnectivity grids that we saw earlier. And then there's actually then transmission lines. So we have the major lines that we saw earlier, and then the smaller lines of transmission. And we see these through the kinds of overhead power lines that you're commonly seeing along roadways. But this is the finer grain of electrical transmission. And by the color chart there, you can see the range of intensity of the power that's being transmitted. It's from relatively low kilovolts to massive amounts, 500 kilovolt lines. And again, these map pretty closely to distribution of population, distribution of industry, and demonstrate areas of growth and development in the country and increasing demands for energy in those regions. Still a lot of active coal mines in the United States, even though they're not producing the material of choice as much as they once were. You can see where they're located through the Appalachian Mountains and into Pennsylvania and in the eastern portion of the United States. This tends to be the dark coal, the black coal that we spoke about earlier. And then scattered sources in the West, which are now primary sources for coal. But this is mostly the brown coal that we talked about, lignite. And these have taken over the lion's share of coal production in the United States. Areas that are reliant on coal for the generation of electricity can map closely along with these sources. You can see that the regions of around the Appalachians, the source of the coal mines, West Virginia, Kentucky, Ohio, Indiana, still heavily reliant on coal. Um, Michigan having a mix between coal and natural gas for electricity production. And as we move out into the West, we see a far less reliance as renewables and solar energy um, are used. Same in the Northeast, where nuclear energy uh, remains one of the bigger players in energy production, along with increasing use of wind. And in the lucky state of Vermont, almost entirely electricity is almost entirely produced by hydroelectric. So it's a complex uh, distribution of sources of energy, as well as the transmission of it when it's converted into electricity. So there's still quite a large number of these coal-fired electrical generation plants, and these are difficult to take offline. Politics as well as technology and our lack of investment in infrastructure both hinder um, the transition from the use of coal-fired plants into plants which use renewable energy sources. Um, Probably more telling in terms of the transition in fossil fuels is the distribution of natural gas electrical production facilities in the United States, which you can see here is um, by and large the largest player in the energy production, electrical production matrix right now. The United States is awash in natural gas, almost to the point where the cost of it are negligible in terms of the overall costs of heating, cooling, producing electricity, and the costs are really in distribution and in the actual production itself. Natural gas might be seen really as a inexpensive, relatively inexpensive in terms of dollar costs, transition from worse fossil fuels such as coal to the renewable energy sources that we aspire to. But it will continue to be a major player in the electrical generation market until our renewable technologies improve and costs related to them drop. Oil distribution, while less crucial to electrical energy production, is worth kind of seeing here to see where Gulf Coast energy production, oil production, and refining remains kind of the main center of such production in the United States, as well as in the plains of the upper Midwest, North Dakota, South Dakota, where new dirty shale oil production is burgeoning. So the advances in oil technology and distribution are moving along apace with the advances in renewable energy production in the United States. And this is a complex monetary and political fight that we're in the midst of. Our switch away from fossil fuels for automobiles is definitely going to play a major role in shifting the balance of this economy. But these companies that make billions of dollars on petroleum development aren't going to give up without a fight. Solar generation, you can see in this map here, I think maps what we might expect, areas that we can expect to have the greatest amount of sun in California, the American Southwest, Arizona, Texas, even New Mexico, are producing huge amounts of electricity from solar. We see a whole cluster of dots in areas that we might not expect there to be so much solar in the mid-Atlantic states, but these also reflect the incentives that our government, local and states, have provided for solar generation, irrespective of the relative lack of sun when we compare to the American Southwest or Florida. But you can see the transmission of electricity from solar generation really kind of reflects the bulk of where it is actually produced, and that's in the Southwest. But you can see that electrical generation from solar from these areas here has a wide transmission into areas far removed from the actual source of the solar power. So this notion of transmission is a key thing to expanding our use of renewable energy to places where it is available, to places where it's not. Wind, as we know, is particularly in Michigan, and is a growth area for electrical generation. And like we saw with solar, you can see from this map that major wind generated electrical power is pretty much distributed by where we expect the places to be the most windy in the United States. West Texas is a huge area of wind electricity generation, powering most of the Dallas-Fort Worth area. And we can see up through the Central Plains where it's the windiest in this country. Is a burgeoning area all the way into Illinois and scattered through areas in the Northeast, again, supported by local subsidies, with offshore wind energy increasing along the coasts of Maine and Massachusetts. Hydroelectric is also a highly distributed energy source. As we spoke about earlier, we're seeing a trend towards smaller dams, smaller investment in smaller hydroelectric production, which can be more nimble. It can have less larger environmental impact, but it's still a niche market for many areas of the country, particularly areas that are flatter. But we see along the mountainous regions in the Northeast, along the Appalachians and along the Pacific coastline, where hydroelectric power continues to be an area of growth in renewable energy production. Nuclear, which began robustly after the Second World War in the 50s and 60s, and then ran into serious opposition from environmental groups, is being looked at again as the first wave of nuclear plants begins to be decommissioned, and new plants are being considered with safer technology. But there's also a change in thinking due to our desire to reduce our carbon output in our energy production. Nuclear power plants are getting a second look, even from environmentalists. So this is a complicated issue due to problems related to, obviously, to nuclear waste. But I think over the next 20 years, we're going to see, with increased demand for electricity, a relook at the capacity of nuclear energy to provide electricity, particularly in our urban areas. You can see in the state of Michigan, we have our own network of electrical grids. We're connected, as you can see on the lower right, to Detroit and up into the thumb of Michigan as part of our electrical grid. And you can see the other areas of the major part of the state is under its own grid from Consumers Energy. And then in the southwest, closer to Chicago, Gary, Indiana, some of the larger industrial areas, that portion of the state is connected with those in Indiana and Illinois. So with that overall sense of the electrical system, introduction to the electrical system in the United States and the production of electricity, let's zoom in a little bit and look at the electrical system in buildings. An electrical system within the context of a building is a network of conductors and equipment designed to carry, distribute, and convert electrical power safely from the point of delivery or generation to various loads around the building that consume the electrical energy. Conductors form a crucial part of this system. Conductors are the means by which electricity is transferred from one place to another. Typically, conductors are made from copper, which offers a good balance between electrical conductivity and cost. Aluminum may also be used in some instances, and these conductors are typically insulated with PVC, materials or other synthetic insulating materials. Most conductors are used in the form of electrical cables that we're familiar with. These can be run either separately or within containment systems, such as conduit or such as other means of combining and isolating the conductors and cables. So some materials, as you know from your basics, right, are good electrical conductors, as we see on the left. Copper being one of the most efficient ones in relationship to its cost. And then a range of insulating materials that we see on the right, which inhibit the transfer and flow of electricity and are used for providing safe installation of an electrical system. Other commonly used electrical systems, we see these all over the art and architecture building, are called bus bars. These are usually copper or aluminum and run within an insulating and safety enclosure, typically called a trunking. We'll see these overhead on the third floor and also down clearly in the fab lab with high electrical consumption there. These bus bar trunkings can be used where larger conductors are required, and it's often physically smaller than the cables of equivalent current carrying capacity. So it's both size and efficiency that drives their use. They're usually made up of rigid lengths and have several tapping points being connecting points for further distribution of the electricity. And here's a couple of overhead shots or let's say an overhead shot of a bus bar trunking, kind of not too different from what we see over our heads in Taubman. And on the left, you can see a segment of that using these bus bars, of copper to transmit electricity rather than the cables or twisted wires that we're familiar with. Switchgear is important in buildings, right? Because this is equipment that provides switching and protection capabilities for the electrical system. They can be both manually or automatically controlled of the current flow. Manual control relies on human intervention. Light switches, right, is a clear system of this. But and they're typically employed for isolating switching and functional switching. We're super familiar with these things. And the nomenclature doesn't really do justice to the common nature of our own interaction with the electrical system in the building. Automatic switching, however, may be based on protection characteristics for devices that detect excess current flow and act to prevent damage to cabling that may lead to fire or electrical shock. At a lower level, we're used to seeing these in terms of plug strips that have a trip on them, fuses that blow, or circuit breakers that we're familiar with tripping when the electrical demand is in excess. We should be familiar with these as architects. Circuit breaker panels are distributed throughout a building for some of the different sub-circuits of the building system. And then each one of these serves a range of outlets or connectivity to equipment and are designed to trip or break the current system in the case of an overload. Switchgear is also automatic and can be handled by control systems where electrical signaling from other relays is used to control devices, known as relays or contactors, which in turn control high-power circuits. These are used to shuffle and redirect energy use at the more macro level within a building or between buildings based on shifting demands of energy use, or in the case of an outage, to redirect energy to prevent the system from breaking apart as a whole as the power is redistributed in the face of local shutdowns. The last part of this is the closest to our own use, and those are load devices, what the terminology is called load devices. These final components of an electrical system convert electrical energy into other forms of energy, such as heat, light, or movement. Examples of these include common items such as light fixtures or luminaires, motors, electrical heating units, as well as power conversion equipment, which converts incoming electricity to lower voltages to run appliances and electronic equipment. Often such power conversion is done within the appliance or load itself. So things we're familiar with, from our washing machine to our KUKA robot to our electric heat pump, all are considered load devices. So with that, we can move on to a quick review of some electricity basics related to power and consumption of electricity. We have two types of current that we use in buildings and in our energy lives in the United States. DC stands for direct current. It's a circuit powered by a battery, for instance, is direct current. Most electronic devices run on DC. Connecting with the analogy of a water in a hose, a DC circuit has all the water flow in one direction. The reason why all the electrical power isn't DC, though, is because it can't be easily transmitted long distances or changed into other voltages to serve different degrees of electrical consumption. So in the early days, electrical power used DC, but required expensive, large diameter wiring and impractical local power generators. Therefore, a more efficient type of electrical power developed, alternating current. When we think about AC, the analogy of the water hose no longer works well. In AC, the current flow reverses direction in a circuit, flowing first in one direction, then in the other. The reversal of flow takes place 60 times in 1 second for typical electrical AC power in America. Thus, AC power is also called 60 cycle or 60 hertz power. The normal AC power in much of the rest of the world is 50 cycles per second. The number of cycles is chosen as mostly an arbitrary standard. There's nothing inherently better about 60 cycles per second or 50, despite what some people might want to tell you. As an aside, lights and motors tend to be designed to work at either 50 cycles or 60 cycles. So one of the reasons why we have these converters when we travel. The wrong frequency in lights causes a flicker, and in motors, more serious problems can occur. Understanding electrical appliances typically designed for one or the other, 60 or 50 cycle power, and will have problems with their efficiency or even safety if the incorrect frequency is used. AC power became the standard throughout the world, mostly because transformers allow AC power to change voltages relative to the need. So utility companies can produce electricity and send it over high voltage lines, say up to 11,000 volts, and simply transform the power to 120 volts for normal use in residential applications. This ability to send high voltage power over transmission lines allows for more power to be sent over smaller diameter cable with less transmission loss than DC power would allow. But many different frequencies of power were initially used when electricity first came into common use. Very early isolated AC generating schemes used arbitrary frequencies based on convenience for a steam engine or a particular application of a water turbine or electrical generator design. All kinds of odd frequencies were in common use at that time, particularly in areas of industrial production that had local energy generation. Some odd frequencies, such as the 87 hertz single phase distribution network, was used in England and all the way into the 20th century. In the early incandescent light period, remember old light bulbs? Single phase AC was common, and typical generators were 8-pole machines that gave a frequency of 133 hertz. So, out of all that mess of different distributed electrical production, two main common frequency of electricity emerged. And there are theories for and urban legends involving this, and there'll be arguments, of course, between Europeans that 50 hertz are somehow better than 60 hertz, but that reminds one of the old Woody Allen movie where his parents debated about which ocean was better, the Atlantic or the Pacific. The German company AEG, still a major electrical power operation in the country, built the first German engineering plant to run at 50 hertz. At the time, AEG had a virtual monopoly, and their standard spread to the rest of Europe. After observing a flicker of the lamps operated at 40 hertz power, AEG raised their standard frequency to 50 hertz. Westinghouse Electric, one of the prime generators of early standardized electrical equipment in the United States, decided to standardize a higher frequency to permit operation of both electrical lighting and induction motors on the same generating system. So the 60 hertz operation allows for a real degree of flexibility and efficiency in different applications. Although 50 hertz was suitable for both, Westinghouse decided that lighting, particularly lighting equipment, operated better at 60 hertz, and so that frequency was chosen. But still, even into the late 19th century, General Electric Corporation, which was affiliated with AEG in Germany, built a generating plant in California that used 50 hertz, but then changed over to 60 hertz production to maintain market share with the Westinghouse standard. So you can see that these large companies actually set standards based on their own particular product, so to speak, that they market, product being electricity in this case. And then these standards become adopted by others within the same electrical grid that we see distributed across the United States. With AC, transformers can be used to step down high transmission voltages to lower customer utilization voltages. The transformer is effectively a voltage conversion device with no moving parts and requires little maintenance. The use of AC has eliminated the need for spinning DC voltage conversion and motor generations that require regular maintenance and monitoring. So it's a very efficient system. And all the more reason why moving towards electrification as our source of power offers a wide range of both space saving and maintenance over more active and more motor and generator source transmission and transformer. Since for a given power level, the dimensions of a transformer are roughly inversely proportional to frequency, a system with many transformers would be more economical at a higher frequency. Another reason why the 60 hertz standard was adopted. So this is a good time to sort of return to where power generating facilities are in the U.S. and thinking about that transmission of power and the efficiencies or lack of efficiencies that come from that distribution. One of the real challenges, as we've talked about, availability and demand facing building electrification goals. And of course, the infrastructure required to distribute that power. Who pays for this? Who controls this? And who has access to it is an important part of our cultural and political debate. Are these to be controlled by private individuals, or is this to be a shared public investment that has shared public benefits? Electrical power transmission over long lines favors lower frequencies, however. The effects of distributed capacitance and inductance of the lines are less at low frequencies. The primary reason for accurate frequency control is the control of the flow of alternating current power from multiple generators throughout the network. This is key to this distributed power generation that we were speaking about. The trend in sequence system frequency is a measure of a mismatch between demand and generation and is a necessary parameter for load control in interconnected systems. This sounds like a lot of pretty technical information, which I admit I am not fully um, uh, understanding of it all, other than we realize what a complex system our local and national energy grids are, and that the demand for standards and equipment to manage from these various sources of energy, the various sources of energy production, electrical production, requires a huge investment in infrastructure to manage and allow these different production resources to be brought together into a collective functioning whole. A couple things just to remind us as consumers about the energy that we use, the electricity that we use. And for many, most of you, these are going to be a review, but worth going through. Voltage is something term we've been using commonly here. Voltage is the pressure that pushes charged electrons through a circuit, much like the water pressure pushing water through a hose. This is what plumbers call head. Voltage is measured in volts. Almost all residential construction in the United States will be 120 volts or 240 volt applications. 120 volts in your basic wall outlet, and 240 for things like perhaps your electrical dryer or your electrical oven or your heat pump. Voltage and frequency in other countries varies, and we'll see in a following map. Current is the strength or intensity at which electricity moves, much like the flow of water in a hose. Current is measured in amps or amperes. We also speak of that as the amperage that a particular application will draw, a particular load will draw. Overcurrent devices such as breakers or fuses and electrical wiring sizes are all based on the amperage of the circuit. 15 amp circuit used to be the common standard for the amount and intensity of electricity on a particular circuit within a building. That has increased to 20 amps in current building construction due to the increased demand for electricity in our buildings. We may see greater changes even then in terms of the necessity to provide more amperage in circuits as our building electrification goals intensify. In residential construction, we're referring to single-family homes at this point. The most common are 100 to 200 amp total main service to the house, with 15 or 20 amp branch circuits supplying electricity to lighting, receptacles, and different zones of a building. As we mentioned, 20 amp branch circuits are becoming the norm. So, there is a big world out there with a lot of different people in it, a lot of different uses, a lot of different demands. And so we see here an overview of the different voltages which are in common use around the world. We see the U.S. Mostly involved with 120 volts, 60 hertz, and large portions of Europe using a 220 or 240 voltage system at 50 hertz. These are, again, we have these converters when we travel overseas so that when we plug into a 240 volt system, we're not toasting our computers or our cell phones or other electrical devices when plugged into higher voltages. Power is a measure of the rate at which energy flows, like the volume of water flowing from a given hose at a specific pressure, voltage, and a hose diameter, amperage. Power is measured in watts. Watts equal voltage times amperage. The pressure times the diameter, let's say, if we keep our water analogy in place, That's the amount of power that is delivered. And the power is what then operates the load, whether it's your light, whether it's your computer, whether it's your toaster. Um, each draw or each require a certain amount of power to operate them, and that power is measured in watts. Resistance is the ease or difficulty of movement with which electrical current passes through a conductor. Materials of greater conductivity, such as copper or aluminum, have less resistance than materials of lesser conductivity, say steel, or no conductivity, such as wood. Resistance is measured in ohms. Energy is analogous to measuring the volume of water that has flowed through the hose over a period of time. Electrical energy is measured in watt hours, or more commonly kilowatt hours. Kilowatt hours, kWh. This is the term we're going to be seeing more of here as the lesson proceeds. A kilowatt equals 1,000 watts, a quantity of power. So here's what kilowatt hour is explained. Kilowatt hours equals watts times time, hours, like the demand, the length of time that power is called upon, and then divided by 1,000 so we can understand it as kilowatts. This is typically how your electrical bill shows up in cents per kilowatt hour. And it becomes a common term for measuring the relative consumption of energy in different buildings, different industrial applications. What can you do with a kilowatt hour? It seems like a kind of an obscure measuring tool if we think of time and energy being brought together into a single term. A kilowatt hour can power a home for 50 minutes. That's pretty interesting. You can run a modern fridge for 20 hours or toast 89 slices of bread. Wow. Toasters are high consumers of electricity. You can power 60-watt light bulbs for 8 hours nonstop, even though we don't really use these anymore. It can drive an electric car 3.6 miles. That's a pretty interesting piece of information. Or it can brew 12 pots of coffee to go with your 89 slices of bread. So you can see some of our appliances really are high consumers of electricity, even though they may be small and somewhat innocuous in our lives. Yeah, that 89 pieces of toast will drive your car 3.6 miles. So how much coal, natural gas, or petroleum is used to generate a kilowatt hour of electricity? This is pretty interesting. It'd say 1.12 pounds of coal will get you 89 pieces of toast, or 3.5 miles in your electric car. 7 cubic feet of natural gas will do the same. Petroleum, liquid, gasoline, an incredibly powerful energy source. Less than 1/10 of a gallon of electricity will toast your morning breakfast and produce coffee for you for nearly 3 months. Petroleum coke, which is a little different than just burning raw coal, is a more efficient source of energy than coal itself, as we see here. So that's our kind of overview of this portion of the lesson. We've looked at the goals of building electrification, some of the opportunities and challenges, the production and distribution of electricity in the national and global energy markets. We've had a brief introduction to electrical system and building, some of the key components and key elements within building an electrical system. And we've briefly reviewed electricity basics, power and consumption. And in the next part of the lesson, we're going to look at key design areas for building electrification efforts.